There we go. All right. This is going to be a charge on a particular atom in a molecule. All right. So for those of you who are missing this, I apologize. I just realized I was going to record this. Now, let's do an example of this. I'll do an example and I'll give you the equation for formal charge. We have a nitrogen, make that a little bit bigger. We have a nitrogen that's surrounded by methyl groups. So the CH3 is going to be a methyl group. This is one of the functional groups you'll learn. All right. So in that case, we have a nitrogen surrounded by 4 methyl groups. If we're going to look at the formal charge, so we calculate the formal charge on the nitrogen. We calculate the formal charge on nitrogen. That formal charge is equal to the number of valence electrons minus the number of non-bonding minus the number the actual numbers 1/2 the number of bonding electrons. So imagine if I had a periodic table here, we looked at the nitrogen, we'd see it's in the 5th column, and therefore, the number of valence electrons that nitrogen has is 5, all right? As we have it drawn here, it does not have any lone pairs of electrons, so the number of non-bonding electrons is 0, all right? Now we have to do 1/2 the number of bonding electrons. So this would be 2, 4, 6, 8. Half of 8 would be 4. And so this would have a formal charge of +1. So this nitrogen would have a formal charge of +1. And I can promise you this, that you'll go through this the first semester and you'll be able to calculate these formal charges without actually doing any calculations. You just look at nitrogen and go, oh, hey, guess what? It's got 4 things bonded to it. It's going to have a formal charge of +1. Oh, look, oxygen has only 1 thing bonded to it. It's going to have a formal charge of -1. And you'll be able to calculate this stuff very quickly. You just get so used to it. We'll do one more. Here we have oxygen bonded with 3 methyls, like that, okay? And we want to do the formal charge now on the oxygen. So we do the formal charge on oxygen. We'll look at our periodic table and see that the oxygen is going to be in the 6th column. So it has 6 valence electrons. The number of non-bonding electrons, so oxygen in this case has 2 non-bonding electrons, so it becomes 2, minus 1/2 the number of bonding electrons, so it's 2, 4, 6, 1/2 of 6 is going to be 3, and so that's equal to +1. So in this case, nitrogen is going to have a formal charge of +1. Now, I apologize, the thing I failed to mention on the previous example is that each one of these methyls is going to have a formal charge of 0. Therefore, the charge of this entire species is going to be +1. So the charge of that entire species is going to be +1 because oxygen happened to have a formal charge of 1, and all the other substituents that surround the oxygen are going to have a formal charge of 0. Let's see here now. Does that make, how are we doing? So far, so good? Mine and David, you getting nightmares from learning this stuff?
No.
No, okay. From a year ago. But you'll be able to do these things really quick. You'll recognize, hey, this only has so many things bonded to it. It can only have this formal charge. Let's see here. So we talked about electron configuration. That is where you look at it's easier if I had a periodic table here. This isn't, now Dr. Baldwin will beat this horse. I can tell you he'll beat this horse to death. He'll talk, well, anyway, we'll get to it a little bit. There are things that are called atomic orbitals. There's things called atomic orbitals. Examples of this are going to be the S, the P, the D, and the F. Remember those? The S is going to be circular. The P is going to be dumbbell shaped. The D is going to be two dumbbell shapes rotated 90 degrees off of one another, or it will be a dumbbell shape with a hula hoop around it. And the F is very similar to that as well, except this will be in 2 dimension. This will be more or less in the 3 dimension. So those are going to be some of the atomic orbitals. From this, we came to electron configuration. Now, if you're having a hard time remembering some of this stuff, go back and look at my notes. Go back and just, you don't have to be, when Dr. Baldwin does this, the nice thing about organic chemistry is it deals with really small atoms. We're not dealing with large atoms. We're dealing with atoms, carbon, nitrogen, hydrogen, and oxygen, very few number of electrons. So you don't have to do these real complex transitional metals with this. So, but if you're having some struggles with this, you don't quite remember this, go back and look at this. But Dr. Baldwin and organic chemistry only deals with the simplest of this stuff. That's the whole basis of this. And so carbon, the electron configuration is going to be 1s2, 2s2, 2p, 2p2. Now, let me make sure it's right. Yes, 2p2 is what that's going to be. So that's going to be a carbon. Fluorine, on the other hand, is going to be 1s2, 2s2, 2p5 is going to be the one for fluorine. All right, if we were to draw this out, this would be 1s, there's your 2, 2s, there's the 2 there, and then the 2p would be as such. All right, so that would be the one for carbon. The one for fluorine, sorry, I have to erase this. The one for fluorine will look very similar. This would be 1s, there's your 2, 2s, there are those. 2p, 1, 2, 3, 4, 5. There's your 2p, 5 for fluorine. Recalling that this is going to be the core level electrons. These are your valence electrons. And these are the ones that participate in bonding. So they're the ones that we find interesting. All right. So far, so good. All right. Now what happens is that these atomic orbitals, what they'll do is they'll actually mix. So these atomic orbitals, these will mix. And what happens is they then generate what are called molecular orbitals. Now, please understand that all this is just some kind of, these are just really models. We're trying to describe what's happening in bonding. And Colin, you'll appreciate this. This all has to do with high-end math. I mean, this is where you come into quantum mechanics. And the equations of this are just massive. They're just huge. So yeah, you'd absolutely hate this stuff. But what we try to do is we try to simplify this. Okay. Now you'll think, oh, this is not all that simple, and it's not. I always find these kind of a little bit confusing. These molecular orbitals, I do try to, they are kind of confusing. They do take some time. All right, let's see here now. So we're just gonna look at the simplest ones, all right? So let's see here. So if we want to look at them for, so we're gonna look at the molecular orbitals for oxygen. Remember, oxygen diatomic, fluorine, and neon. All right. Now I'm just going to draw the molecular orbital. All right. So there's a molecular orbital. I'm simply going to draw the diagram. Now, Dr. Baldwin will talk about this. Now, Colin, we skipped this because the majority of your class was not going to take organic chemistry. They were going to go off and attempt to become engineers. So it was only going to be you and Carter that were actually going to use this. So this, you'll want to maybe do a little review on this, but don't get freaked out about it because it's fairly intimidating and kind of ugly looking. I always have to write notes for it because I always forget how to draw these silly things. And what this is where this is a mix of atomic orbitals. It's as though the atomic orbitals mix, or as though the atomic orbitals marry and reproduce. Those atomic orbitals will then reproduce what are called atomic orbitals. All right. Now these atomic orbitals are really nice because they are able to predict both physical and chemical characteristics of molecules that atomic orbital theory is not able to do. So therefore, can you see that way down there? I'm going to tip this down. Oh, you can't see it. All right. Now down here, this would be what's called a 1 sigma. And this 1 sigma is going to be made by mixing up the 1s atomic orbital. So now this is the atomic orbital. This, the sigma, so that the English letter is the atomic orbital, the Greek letter is the molecular orbital. All right. Now this is a bonding orbital. This is a bonding orbital, and I'll show you very soon how we distinguish between bonding and what's called anti-bonding. All right. The next orbital up here is a 1 sigma 1s, and we put the star there. Now the star, this star indicates anti-bonding. And what we do is we put electrons in here just like we did with atomic orbitals. So remember, or just like we did with electron configuration, you start putting electrons in here. Now, if you put electrons into this anti-bonding, what that means is it's trying to break apart. It's trying to break apart that bond. Does that make sense? It's trying not to bond. It's not stable. Once you start putting electrons in here, the molecule is not stable and wants to break apart. Okay. The next level we got is going to be up here, and this is 2 sigma, and this is formed by the 2s. And then up here we have the 2 sigma star 2s. Okay. right? Now is where it gets confusing, all right? So this is a formation. So these molecular orbitals are formed by the 2s atomic orbitals. Now this is where it gets confusing, if it isn't confusing already. Up here, we have what we call the, oops, see, I'm already getting confused, see? This is now the 2 sigma 2p. So this is the 2 sigma bond formed by a 2p electron. Then up here, we've got the 2 pi 2p electron. Then up here, we have 2 pi star 2p. Okay. And then since we have a notice kind of a pattern, we have a sigma, sigma star, sigma, sigma star, sigma, oops, we don't have a sigma star yet, we have a pi and a pi star. So up here, this is going to be then 2 sigma star 2p. And once again, these stars indicate anti-binding orbitals, such that when electrons are placed in there, the molecule is not stable. Okay. Now, these two switch for boron, carbon, oops, right this way, boron, carbon, and nitrogen. So far, so good. It gets fairly confusing. Now, here's where here's where kind of the point of this is. We're still on molecular orbitals. We can have what are called LUMOs. We'll start with the LUMO. All right, so LUMO, this is just simply an acronym. This is the lowest unoccupied molecular orbital. Then we can have what's called the HOMO. Well, that stands for where this is the lowest, L is the lowest, and this is unoccupied. This is going to be the highest occupied molecular orbital. All right. So Dr. Baldwin, I can promise you, will talk about some of this stuff. This is really not a big deal in organic. I mean, it's not a huge deal in organic chemistry. It becomes a much larger ordeal in inorganic chemistry, minus since you're looking at biochemistry or a chemistry major. This becomes a little bit bigger deal in inorganic chemistries where this gets talked about quite a bit, but not so much in organic chemistry. I mean, you'll hear some of it. He'll talk about the HOMO and the LUMO. Just understand that the LUMO is the lowest unoccupied, so it'll be the level which does not have any electrons in it. When we talk about being occupied, we're talking about it being filled or having some kind of occupancy for an electron. All right. So far, so good. Now, Now we're going to talk about something that's going to become important to you. This would be something you'll see quite a bit. You should probably pretty much already know this. But once again, this is just simply going to be a review. You're going to find out that the first, at least the first 2-3 chapters we do here, it's just going to be a review. You know, oh man, we've already seen this. Yes, that's exactly what I see. And I'm going to be completely honest with you. When I was at Winona State, that's the school I was at before. It's a big school in Minnesota. We did what's called a DUC exam. So that stands for DUC stands for Diagnostic Undergraduate Chemistry Knowledge Exam. We gave it to our seniors. And the seniors always fell off. They did amazing on the exam, except when it came to the basis or the basics of organic chemistry. What screws you people up, and I'll be completely brutally honest with you, is your lack of retaining and understanding the fundamental things we learned in Chem 1 and Chem 2. Dead serious. Baldwin will come into my office, I guarantee, in week 2 and say, what's wrong with these students? Didn't you teach this stuff? Yes, I taught this stuff. You just don't retain it and you don't realize you have to use it for this course. So for the first couple of weeks, with the exception of you, Con, because you saw pretty much about all this, except when we start talking about intermolecular forces, and that's really easy. Is this the idea of an acid and bases? You didn't see acids and bases. Is that if you really get the fundamentals down, it's just like even a sport, right? You get the fundamentals down, you're going to do really well. So a lot of this, you're going to go, oh, we've already seen it before. Just keep reviewing it, keep reviewing it, keep reviewing it. Because organic chemistry is a lot like biology, where the ideas of biology are mind-numbingly simple. They're not that complex. But you study a really complex system. And that's what makes biology complicated and difficult. Same thing with organic chemistry. The ideas of organic chemistry, I'll say it 1,000 times probably while I talk to you people this summer, are mind-numbingly simple. They're not hard. They're really easy if you know your fundamentals. But you're going to apply it to really complex systems that are going to trip you up. And that's just how it is. It's why I didn't like organic chemistry in the first place. All right. So now we're going to talk about hybridization. All right. Now, Dr. Baldwin will go through all this difficult stuff for you. I'll do one example of the difficult stuff, and then I'm going to show you how to get the stuff really easy. All right, we're going to. None of you have had calculus. That's too bad. There's a great analogy of this. So hybridization, what this is a combination of two or more atomic orbitals. And then these form hybrid. And what this is going to get to, and mine and David have heard this 1,000 times from me, maybe you have too, Colin, is that this is ultimately going to get us to the geometry. We're going to get to some kind of geometry of this molecule, which is going to lead to polarization. Is it polar, non-polar, that kind of thing, all right? So if we look at something that's going to be sp3, what we're saying is that we have one s mixing with 3p orbitals. So how many orbitals do we have in total? We have 4. So this is going to come up with 4 orbitals. So this would be your sp3. All right. For example, an example of this would be carbon. Carbon is that's what we're going to be talking about. That's what you're going to talk about this entire semester or year is going to be carbon. So for example, carbon, that's going to be 2s to 2p2. Now we can break these up into 1, 2, 3, 4. Right? So we could look at an sp3, so it'd be 1, 2, 3, 4. We have 4 electrons. If we have an sp3, that means that one of these is going to be an s, 3 of them are going to be a p, so they'll mix to get an sp3, so they'll become 4 atomic orbitals. Or we can say if this is 4 unpaired electrons. So what the sp3, what one of them looks like, well, what this means that then the center atom will have 4 things bonded to it. So an example of this would be methane. All right, so this would be carbon. I'm going to attempt to draw this, but you know my drawing abilities really stink. All right, and then here would be the hydrogens. Now the shape of this is tetrahedral, and that's the easy cheat to this, is going to be tetrahedral. I could spell, but I can't. It's going to be tetrahedral. The bond angle is 109.5 degrees. All right. So here's the dirty cheat. This is the copy. This is the, you know, I always say, oh, there's got to be some kind of trick. Here's the trick. If it's tetrahedral, it's sp3. That's it. It's sp3. Okay? That's the trick. All right. Now, next we'll look at will be sp2. sp2 will be 1s. This will be 1s and then 2 p's. All right. Now this has 3 orbitals, right? 1, 2, 3. This, an example, this would be boron, trifluoride, that will have a bond angle of 120 degrees, all right? And this will be trigonal planar. That'll be trigonal planar. Now, another example of this is going to be ethylene. So ethylene is a neat compound. It's a compound that is given off naturally in fruits and vegetables. It causes them to actually ripen. So if we were to draw this molecule, if you look at each carbon, all right, so for example, if you look at each carbon, we're going to make one green and one red. Right. If we look at this carbon right here, there's one carbon there. There's another carbon. And what we can do now is if we look at this green carbon here, how many things are bonded to it? Well, it's going to have 1, 2, 3. That carbon has 3 things bonded to it. It's going to be trigonal planar. So this carbon right there is going to be sp2. All right. Now, if we look at this carbon, the red carbon, how many things does it have bonded to it? Well, it has 1 carbon bonded to it. It has 2 hydrogens bonded to it. So this one red carbon has 1, 2, oops, I can't count, it's 2 stinking around. 1, 2, 3 things bonded to it as well. So therefore, this carbon is going to be sp2 as well. All right. And then lastly, so even within a molecule, carbons can have their own hybridization. So for example, acetic acid, one of the carbons is sp2, the other carbon is sp3, right? So within a molecule, the carbons can have different hybridizations, and that's perfectly fine. And the last hybridization we have is going to be sp. Now that's going to be 1s and 1p. And that's going to lend us to 2 atomic orbitals. And an example of that is going to be acetylene. So acetylene is an example of that. And this is carbon 1, 2, 3, carbon, hydrogen, hydrogen. Once again, each one of these carbons has, if we look at, we're once going to do the red-green trick. We'll make this carbon all right. This carbon here is 2 things bonded to it. That will be sp. This red carbon has 1 carbon bonded to it and another hydrogen. That's going to be sp. And more importantly, is that this is a linear molecule. That's a linear molecule. In the previous example, if it's going to be sp2, it's going to be trigonoplanar. So now, what we can do is we can look at a different molecule, right? And we'll look at the acetic acid one, because that's really a nice classic one to look at. Here we'll have a carbon bonded to another carbon, right? Oops, I don't have hydrogen. So which one do you, which carbon is, all right, what is the hybridization of this carbon? How many things are bonded to this carbon?
4.
4, exactly. So the hybridization is going to be?
sp3.
Exactly. This is sp3. And what's the geometry going to be?
Tetrahedral.
Exactly. This red carbon has how many things bonded to it?
3.
3, yep. So it's going to be sp2, and it is trigonoplanar. And you'll see this quite a bit. You'll see this one quite a bit. This is called a carbonyl, just that group. This is called carboxylic acid, but this is a carbonyl. You'll see this one a lot, and they take they'll take advantage of that quite a bit. All right. 7, 8. And just due to time, another thing you're going to look up will be valence shell electron pair repulsion. This is also VSEPR. This is how electrons do not want to be near one another. They want to be as far away from each other as possible. And then let's see here. That would be something you want to look up. That's pretty easy stuff. We've done that as well. We did quite a bit of VSEPR in Chem 1. All right. Now, the last thing, and we've talked about this a little bit, but not a whole lot, is bond length and bond strength. Okay? So, for example, here we have a single bond. This is called an alkane. Okay? is a double bond. This is called an alkene. All right, this is cane-ene. And then we have a triple bond. This is called an alkyne. All right. Now, as we go from here this way, there's an increase in bond strength. So there's an increase in, and in this case, we're looking at the carbon bond is what we're looking at. All right. So it only makes sense that a single bond is going to be lowest in strength compared to a double and a triple bond. All right. Now, if we go in this direction, we go in the opposite direction. We go in that direction. There's an increase in bond length, such that the single bond is going to be longer than the double bond, which is going to be longer than the triple bond. Does that make sense? We can also now go a little bit further here, and we could say, well, this is an sp3, this is an sp2, and this is going to be an sp. So we can include that as well too. And in this case, what we're looking at in the red is we're looking at the carbon-hydrogen bond. All right. All right. Now we'll get that out of there. But there we're looking at those carbons. So far, so good. All right, that's an hour. And that's basically the first chapter. If you have any, you have any questions? Well, hopefully this will be helpful. What days and times work best for you folks? Does this time work
Days
well?
work for me.
Does this
Yeah,
work for you?
same. Mhm.
How about
Yeah,
you,
for me
Mina?
too.
I'm good with this time too. So.
Okay. All right. Thursday. We're not gonna get through all of organic 1. My goal is just to, if I could get up to stereochemistry, that would be great. That's hard stuff. But ultimately, I said that this is all about functional groups. If you can also, the functional groups are a big deal, right? Because that's how all these books are actually organized by functional groups. But ultimately, as I said, you can look at all of organic chemistry in terms of electronegativity and acid-base chemistry. Now that becomes a little bit more specific, and they call this SN1, SN2, E1, E2. So SN1 stands for substitution, nucleophilic substitution first order. SN2 is nucleophilic substitution second order. E1 is first order elimination. E2 is second order elimination. That has to deal with kinetics, but you don't actually look at the kinetics. That's really the heart of organic chemistry. And then in there, we'll also be able to we'll look at hopefully we'll get some time to look at alkyl halides. But if you've got this book, hopefully you've got the book. It's a very simple book to read. There is not many words to it. That Janice Smith book, it's actually the book that taught me organic chemistry. But most organic chemists hate the book because it's poorly organized. If she would organize a little bit better, I think it'd be probably the best organic book out there, but it's so terribly organized. It's terrible. So, all right. So I hopefully we'll see you guys on Thursday. If you have questions, let me know. All right. Don't be afraid to reach out to me. My in-laws are here for another 19 more days, not that I'm counting, I am counting. So I'll be at work every day unless I'm fishing, so that's pretty much it. All right?
Yeah, thank you.
And David, I'm gonna be here, so if you wanna get here earlier than 7:45, I'm joking. Have any questions, let me know. All right? Colin will go fishing sometime, when you get some time off.
All right, I'll let you know in the next couple weeks. I haven't got my
Fine.
schedule yet.
That's fine. My in-laws leave the 25th, so. Not that I'm happy or anything, but anyway. All right,
Great.
talk to you later.
Yep, we'll see you.
Bye.